begin the training session shortly. Please note that the session will be recorded and then shared with all participants via email that has been used for registering. I would like to start the session with a land acknowledgement. As treaty peoples, we all share a duty to respect and give care to the territories that we live on and honor the many treaties and agreements that govern the land. From time immemorial, indigenous nations have coexisted on these lands where we all now reside and have been forming relationships both among nations and with the lands and waters that support them, and upholding treaties which continue to have importance to this day. So we acknowledge and respect the ancestors and current caretakers of these territories, as well as our own individual responsibilities under all existing treaties. We're all in different parts of the province now. Here in Ottawa, I'm on the traditional and ceded territory of the Algonquin Anishinaabe people that have lived on this land since time immemorial, and I'm grateful to have the opportunity to present in this territory. I would also like to acknowledge the Ontario Ministry of Agriculture, Food and Rural Affairs for supporting the development and delivery of this training session. The session will highlight research that has been conducted over the past 2 years with engagement of the Council of the Great Lakes region and financial support from Bruce Power. A few words of introduction for the Climate Risk Institute team that will be hosting and facilitating today's session. My name is Anna Zaitseva, and I'm an advisory and technical services liaison at CRI with a background in climate science, geospatial technologies, and conducting multiple climate change risk and impact assessments, a lot of them in the agricultural sector. Paul Cobb is the manager of training services at CRI, who has worked over 20 years in the fields of climate change mitigation and adaptation, and he's now coordinating CRI's work with multiple partners and experts to develop and deliver professional development programs for engineers, planners, and other professionals. Alyssa Hill is a climate change adaptation and resiliency analyst at CRI. She holds a master's degree in climate change, and through her studies and also work experience has been involved in initiatives related to climate action, equity, and sustainability, as well as climate change adaptation, mitigation, and governance in Canada. Please feel free and welcome to introduce yourselves in the meeting chat as well. At today's session, we will go over a number of themes related to vulnerability assessment and adaptation response planning in the agricultural context. We will start with a brief overview of past risk assessment work that we conducted over the last 2 years in Grey, Bruce, and Huron counties, followed by looking at climate trends, hazards, and impacts relevant for agriculture, as well as more broadly. We will then explore existing opportunities, as well as vulnerabilities, specifically crop sensitivity and exposure to climate hazards, review the concepts of adaptive capacity and resilience, and also discuss adaptation responses and best management practices relevant for field crop production in the region. We will have a pause about halfway through the session to reflect on the presented material, and we'll finish with a hands-on group activity on critical evaluation of existing and possible future risks and vulnerabilities in cash crop farming and identifying on-farm response measures. Throughout this training session, please feel free to add your questions to the chat box. We will be pausing to answer them at a number of points during the presentation. Objectives of today's session include being able to better understand current and future risks to cash crop production, have increased awareness of climate change vulnerability and factors that influence it, and be able to make informed decisions on applying recommended responses and adopting best management practices to mitigate climate risks. As we go through the topics in the agenda, references will be made to the research conducted over the past 2 years that I mentioned with engagement of Council of the Great Lakes region and Bruce Power. We will draw from the assessment's results to talk about whether trends and projections, key impacts, vulnerabilities, and possible adaptation actions, as well as best management practices to improve the resilience of the ag sector in the region to the changing climate. Risk assessment is one of the components of adaptation planning. Risk assessments are important because they are a practical tool to understand what and who is at risk. And understanding risk does require some engagement, the need to understand people's values and perceptions of risk. There are 5 steps in the risk assessment process. First, you identify the problem that you're considering. Then you look at what are the key hazards in the scenario. What is the exposure of the receptor to the hazard? After that, looking at the consequence of exposure to the hazard, so the exposure-consequence relationship. And lastly, look at the risk and what are the options to mitigate the risk or adapt to the risk. Some general considerations that are applicable to multiple steps include communication, documentation, and reporting, using existing resources and local knowledge, and also ensuring education and awareness of the audience. As with any risk assessment, the goal of our work was to understand potential climate-related risks and help stakeholders make informed decisions about adaptation. The map here shows the study area within Southern Ontario that includes Grey Bruce and Huron counties, located on the coast of Lake Huron and Georgian Bay. Agriculture is an important industry in the region, and main commodities include cattle and calves, dairy, also soybeans, corn, and poultry. Specialty crops like apples are also grown primarily in Grey County. There are regional differences both in crop and livestock production that reflect the soil and climate characteristics of the region. Through the risk assessment, our team has assembled and reviewed literature on climate change vulnerabilities, opportunities, and risks, and developed risk scenarios to capture current and projected risks to different components of the agricultural sector. Interviews with the local stakeholders were held to help us better understand the effects of climate in the study area and inform the risk registry. We have presented our main findings from literature and interviews at a workshop, and then discussed options for priority climate risk and information products, and then developed a series of risk products with feedback we have received from the stakeholders. For the purposes of the assessment, risk was identified as potential for consequences where something of value is at stake and where the outcome is uncertain. The risk of climate-related impacts results from the interaction climate-related hazards, including hazardous events and trends, with the vulnerability and exposure of human and natural system. So climate impact pathway begins with climate hazards like drought or extreme rainfall that impact agriculture components, for example, crops or farm infrastructure, and that can have consequences across multiple categories, for example, financial loss and environmental damage. As shown in the bottom figure, risk is the product of the system's exposure to a hazard, and its magnitude is linked to the likelihood of the hazard occurring and the severity of the consequence. Gathering information about risk is a key element of the work. Quantitative data can be used for statistical analysis and probability assessment. There's also community knowledge and experience that can be equally important in this process. Some examples of critical data sources include climate data portals, literature, past events and community experience, as well as operational experience, local traditional knowledge, observations from site visits, and professional judgment. So to summarize, it is important to remember that data about risk comes from many sources. It is advised to use quantitative data where possible, keeping in mind that qualitative data is also very valuable. In Grey, Bruce, and Huron agriculture risk assessment, we engaged with local stakeholders and asked questions about their experience with weather, climate, and issues they have experienced or anticipate. Weather variability was a common trend that was mentioned. While farmers have always needed to adapt to natural weather cycles, conditions are becoming more variable and extreme over time. For example, in recent years, many have noted that they experienced flash flooding followed by drought conditions. And this variability makes it harder to plan and can mean that there is less time to get everything done. Many participants also noted frequent and intense storms, high winds, a great prevalence of pests, or changes in pest distributions. Some of the other topics that were brought up less frequently, but are still relevant, include warming temperatures, drought, earlier fall or later spring frost, and also increasing freeze-thaw cycles. As we discussed, these weather and climate changes, the most frequently referenced area of concern was water management, which encompassed a lot of different impacts like increased runoff, legacy phosphorus, and flooding. We also heard frequently about soil erosion and poor soil health, including impacts to topsoil and nutrient losses. Some of the areas of concern overlap with the climate and weather impacts noted earlier in the previous slide. For example, drought conditions that occurred during the growing season or flooding events, leading to increased erosion. Having identified major hazards and impacts, we used information on climate variables, agricultural sector components, and vulnerabilities to develop risk scenarios that were then assessed for the degree of current and future risk. These scenarios consider how a climate hazard can cascade to direct and indirect impacts for different subsectors. Climate indicators are used to describe how a climate hazard can be represented during using weather and climate data, so that projections can be made for future climate change. Components can be impacted differently. For example, frost conditions affecting winter wheat and apple trees are different, which has been reflected in the scenarios by using different climate thresholds. Once the scenarios were developed and assigned, the likelihood and the consequences of each event and the impact on the event was done. The consequence categories we included are financial losses, environmental damage, infrastructure damage, and service disruption, and also human health and public safety. The magnitude of risk is the product of the likelihood of hazard occurring and the severity of consequence. Significant increases in heavy precipitation and flooding events affect field crops and also farm operations, soil and water resources, with the risks expected to increase in the future. Heavy precipitation events during the growing season cause increased runoff, leaching of nutrients and chemicals, water contamination, also degraded soil quality, waterlogging, and erosion, causing damage to crops and infrastructure, and also delays to planting and harvesting operations. For heat, exposure to temperatures over 30 degrees is detrimental to most crops. Heat stress results in shortened phenological stages, greater susceptibility to diseases, and reduced yields in crops. For drought conditions, during the summer months, they can adversely affect water resources and soil quality, with significant implications for field crops. Financial losses due to crop damage and environmental degradation, as well as public health concerns, are the main consequences that contribute to overall risk scores. That, as we can see, they largely fall into moderate and high risk categories. The assessment found that there are a few instances where the changing climate could present opportunities for field crop production, driven by longer growing seasons, milder winters, and fewer frost days. However, the assessment found that any benefits are likely to be offset by the risks associated with increased frequency and intensity of extreme weather events, variability in seasonal temperatures, and changing precipitation patterns at critical crop development phases. Additionally, indirect climate impacts to field crop production, including impacts to water management and soil health, introduce another layer of complexity that influences how climate impacts can cascade within and across the region. Some key lessons that we've learned are that key impacts to agricultural production are caused by drought, extreme precipitation, and heat events, that information on risk needs to be supported with information on solutions, and that climate risk products, in order to be most beneficial and useful, need to raise awareness, support planning and design, and support implementation of resilience measures. We have developed a number of climate risk products as part of the risk assessment, including a risk registry, climate risk infographics, and case study series on best management practices in agriculture. Over the next several slides, we will review key climate trends, hazards, and impacts in Ontario, focusing on the agricultural sector. We will begin talking about these fundamental concepts by looking at what climate is, how it is different from weather, and what we refer to when we say climate change. Weather is a short-term state of the atmosphere and can change within minutes to hours. In a narrow sense, climate is usually defined as average weather or a long-term pattern of weather. More rigorously, it is the statistical description of weather over a period of time, specifically the mean and variability of relevant quantities, for example, temperature and precipitation, over a period of time that ranges from months to thousands or millions of years. A classical period for averaging these variables is 30 years, as defined by the World Meteorological Organization. Climate change is what happens when the mean and the variability shift due to either natural internal processes, such as volcanic eruptions or solar cycles, or external forces, including anthropogenic forcings. These include emissions of greenhouse gases, changes in land use affecting things, such as soils, wetlands, and forests. What would we expect if climate was warming? In the image here, you can see some key indicators of global change: water vapor in the atmosphere, temperature over land, ice and snow cover. In a warming climate, we would expect to see increasing or decreasing trends in each of these indicators, such as increasing sea level and sea temperature, and decreasing sea ice. And in fact, this is what we have already observed. All current observations reinforce expectations of warming and climate modeling. There is reliable, measurable physical evidence that supports our understanding of the climate system. In the following sections, we will focus on how exactly Canada's climate is changing, focusing specifically on Ontario's climate. However, it is worth taking a moment to remember that across Canada and around the world, the impacts of climate change can be different, and for many people around the world, they are an existential threat. There are at least two elements to this. So first, the importance of collective action on mitigation and emissions to reduce harms. And then it's important to remember that Ontario residents will be affected by not just impacts that happen locally, but by national and international impacts of climate change. Food security and supply chain are some examples where climate change poses risks and can have significant implications to Ontario residents. So looking at Canada's changing climate, starting at the national level, there has been evidence gathered on warming in the country. Canada has already warmed and will continue to warm at about double the global rate. The oceans are warming, becoming more acidic and containing less oxygen. The effects of widespread warming are evident and projected to intensify. Total precipitation is projected to increase on average, with decreases in snowfall and increases in rain. Summer rainfalls may decrease in some areas as well. The seasonal availability of fresh water is changing, with an increased risk of water supply shortages in the summer. Weather extremes are expected to intensify in the future, and the rate and magnitude of climate change under high versus low emission scenarios project two very different futures for Canada. An immediate reaction might be, what difference does a degree or two change in average temperature or a 10% increase in annual precipitation make? When the average or mean value increases, that means that the frequency of what we historically understand as extremes is also increasing. Additionally, we see extremes that are more severe than we previously prepared for. This long tail of extremes is where many high consequence risks can be found. Frequency and intensity of extreme weather events have been increasing, and this trend is expected to continue. And a lot of research focuses on anthropogenic influences on the probability of particular weather events, as well as their strength and intensity. So we are to expect, to summarize, fewer cold extremes, more heat extremes, and in particular, more record-breaking heat extremes with significant implications on different sectors, including agriculture. Ontario's temperature has measurably increased already compared to recent baseline records and periods. This is true for both averages and extreme variables. The other important notes is that winter temperatures have been increasing at a greater rate than summer temperatures. For instance, in Owen Sound, the number of days per year over 30 degrees will increase from 8 to over 19 by mid-century, compared to 1991 to 2020. With regard to precipitation, we see higher or lower levels of change depending on geography. For example, including how far north the community is and also its proximity to the Great Lakes. It's also not uniform by season. Most increases in precipitation happen in winter and fall. So what we have seen so far in Ontario is that annual precipitation is increasing with seasonal variability, highest increases being recorded in winter, with more precipitation falling as rain, especially in the south of the province. Some precipitation projections show an overall increase in precipitation, again, concentrated in fall and winter. Summers are projected to become drier, with important regional considerations that include increased lake effect, snow and rain. Dry summers and higher intensity rainfall can lead to a variety of impacts, such as flooding and erosion. Welcome everyone who has joined our session today. I'm Anna Zaitseva, and me and my colleague Alyssa here represent the Climate Risk Institute, and we're very happy that you were able to join us. We will begin the session with a land acknowledgement. So I just wanted to say that as treaty peoples, we share a duty to respect and give care to the territories that we live on and honor the many treaties and agreements that govern the land. From time immemorial, Indigenous nations have coexisted on these lands where we now all reside, forming relationships both among nations and with the lands and waters that support them, and upholding treaties which continue to have importance to this day. And we acknowledge and respect the ancestors and current caretakers of the territories. as well as our individual responsibilities under all existing treaties. I know we are likely in different parts of the province, and here in Ottawa, I'm on the traditional unceded territory of the Algonquin Anishinaabe people who have lived on the land since time immemorial, and I'm grateful for the opportunity to present in the territory. Before we continue, I would also like to acknowledge the Ontario Ministry of Agriculture, Food and Rural Affairs for supporting the development and delivery of the session, which will in part also highlight research made possible by the engagement of the Council of the Great Lakes region with funding from Bruce Power. So a few words about our team that will be hosting the session. So I'm Anna Zaitseva, an advisory and technical services liaison at CRI, and my background is in climate science, geospatial technologies, and also risk assessments, a lot of them conducted for the agricultural sector, and I'm the project lead on this project. Alyssa Hill is my colleague who has been providing support on the project. She has a master's degree in climate change and has, through her studies and work experience, been involved in initiatives related to climate action, sustainability, and also climate adaptation and mitigation. So as we are a small group today, I would ask you to go ahead and unmute yourself and introduce yourself, say a few words about who you are and where, what organization you represent.
So I'm Shannon Stevens. I'm the Healthy Waters Program Coordinator in the Nottawasaga watershed, which is to the west of you a bit from Ottawa, so west of Lake Simcoe, north of Toronto. And we have 3 counties we cover, including a small bit of Grey, Dufferin, and Simcoe counties, and we drain out into Georgian Bay. Okay. And I work with farmers. I work with farmers a lot to do habitat and water quality improvement projects to implement best management practices on the properties. So, excellent.
Yeah, this is something that we will cover during today's session for sure. The best management practices and resilience and adaptation measures. Nancy, would you say a couple of words to introduce yourself as well, please?
Hi, I'm Nancy Chan, and I'm with Osenko Sustainability. I'm located in BC, but we do work across the country. I have next to zero experience with agriculture, but I'm here to learn.
Excellent. Thank you so much for joining. Yes, and I'm hoping that this session will be helpful and provide some learning opportunities. So some of the things that we will cover today are, we'll begin just generally with an overview of climate trends, hazards, and impacts that are of importance. Some of them broadly for Canada, but mostly for Ontario and specifically for southwestern Ontario, so Grey, Bruce, and Huron counties. So Shannon, that would be closer to where you are, right? So along the coast of Lake Huron and Georgian Bay. We'll talk about existing vulnerabilities, focusing specifically on livestock sensitivity and exposure to climate hazards. We will also discuss adaptive capacity and resilience, as well as adaptation responses and best management practices. And then we will wrap up our session with a group activity, so a bit of a discussion of a fictional scenario. Throughout the session, please feel free to add your questions either to the chat box or raise your hand and we'll pause to answer your questions as we go along. So following this session, the achievement would be a better understanding of current and future risks to livestock production, increased awareness of climate change vulnerability and factors that influence it, and also more ability to make informed decisions on applying recommended responses, adopting best management practices to mitigate climate risks. So as we go through the topics that we've just seen in the agenda, references will be made to research that was conducted over the past 2 years with support from Bruce Power and Council of the Great Lakes region So we will draw from assessment results to talk about weather trends, projections, and also key impacts and vulnerabilities, and possible adaptation actions and best management practices to improve the resilience of the ag sector in the region. So briefly about the risk assessment, it's one of the components of adaptation planning, and risk assessments are important because they are a very practical tool to understand what and who is at risk. Understanding risks also importantly requires some engagement. They need to understand people's values and perceptions of risk. The 5 steps in the risk assessment process include, so we start with identifying the problem. So what is it that we're considering? Looking at the hazards for the scenarios, the exposure of the receptor to the hazard, and also the consequence of that exposure. Ending it with defining and assessing the risk and looking at the options to mitigate the risk. So some general considerations that are applicable to most of those steps are communication and reporting, using existing resources and local knowledge, and also ensuring the education and awareness of the audience. So as with any assessment, the goal of our work was to understand potential climate-related risks and help stakeholders make informed decisions about adaptation. So the map shows the region where the assessment was conducted. The agriculture is obviously an important industry in the region, so mainly focusing on livestock as well as cash crops, and there are regional differences both to crop and livestock production that reflect soil and climate characteristics in the region. And so through our work, we have obviously we have reviewed literature, developed risk scenarios, engaged with the farmers, conservation authorities, and other stakeholders in the region, and developed a number of risk products to inform stakeholders about the key issues that we have found and the solutions to those issues. So the way we looked at risk was define it as a potential for consequences where something of value is at stake and the outcome is not certain. So the climate impact pathway here begins with climate hazards like drought or extreme rainfall that impact agriculture components like crops, livestock, and infrastructure, and then the impacts kind of consequences across multiple categories like financial loss and environmental damage. And so as shown in the bottom there, the risk is the product of the system's exposure to a hazard, and the magnitude of risk is linked to the likelihood of that hazard occurring and the severity of the consequence. Gathering information about risk is important, so looking at quantitative data like climate data specifically for statistical analysis, also drawing from community knowledge and experience. And so we've covered most of this in our work. So looking at past events, operational experience, local traditional knowledge, and professional judgment. It's important to remember that data about risk come from different sources. And so while it's advised to use quantitative data where possible, qualitative data is also a lot of times very valuable. So in our assessment, we engaged with local stakeholders and asked them questions about their experience with weather, any issues that they have experienced or anticipate in the future. One of the common things that they mentioned was weather variability. So while the farmers need to adapt to natural weather cycles on an ongoing basis, conditions are becoming more variable and extreme over time. For example, many noted in recent years, they've experienced flash flooding followed by drought conditions. And this variability makes it harder to plan and can mean that there's less time to get everything done. Many of the participants also noted frequent and extreme storms and high winds, as well as a growing number of freeze-thaw cycles. as some of the concerns. Additionally, as we discussed weather and climate changes, the most frequently referenced area of concern was water management, which encompassed a lot of different impacts like increased runoff, flooding, legacy phosphorus, and we also frequently heard about soil erosion as well and poor soil health. So having identified major hazards, we used that information on climate variables and ag sector components and vulnerabilities to develop risk scenarios that were assessed for the degree of current and future risk. So they consider how a climate hazard can cascade to direct and indirect impacts to different subsectors. And we used specific thresholds for different scenarios depending on the key element that was involved. So here, for example, we see that extreme heat affects dairy and poultry in a different way, and tolerance thresholds vary. That has been reflected. So poultry is more sensitive to extreme temperatures. So once scenarios have been developed, we have assigned the likelihood of each event occurring and the consequences of the impact of the event, including financial losses and environmental damage. And we looked at both historic and future timeframes. So here briefly, some of the biggest risks were related to precipitation, which affected both crops, soil and water quality, as well as livestock, followed by heat-related risks, which was the major concern for livestock in particular, and also drought-related risk, which was relevant for crops and also livestock, and specifically indirectly impacting livestock through quality and availability of feed and quality of pasture. So to summarize here, as I said, so drought, extreme precipitation, and heat caused major impacts. We also learned that information on risks needs to be supported with information on solutions, and climate risk products of the highest value need to raise awareness of the issue, support planning and design, as well as implementation and adaptation. And so some of the products we have developed, and we'd be happy to share those with you, are, so there's the risk registry, climate risk infographics, focusing on hazards and trends, as well as key hazards and risks, and also a series of case studies on best management practices in agriculture, focusing on not just BMPs, but also alternative land use services, or LS. So that was a kind of a brief overview of work that we've done. And over the next slides, we will review key climate trends, hazards and impacts in Ontario with a focus on the ag sector. And again, I encourage you to ask questions in the chat or raise your hand if there are any questions. So here we'll briefly talk about climate change fundamentals, just looking at what is climate and how it's different from weather. So weather is a short-term state of the atmosphere, and it can change from minutes to hours. Climate, in a narrow sense, is usually defined as the average weather or a long-term pattern of weather. And more rigorously, it's the statistical description of weather over a period of time. So we talk about the mean and variability of relevant quantities like temperature and precipitation over a period of time that can range from months to thousands or even millions of years. Climate change is when the mean and variability shift, either due to natural processes or external forces. So natural processes would be solar cycles or volcanic eruptions, with external forces including anthropogenic forces like greenhouse gas emissions, and also changes in land use that affect carbon sinks. So what would we expect if the climate is warming? So in the image here, you see some key indicators of global change, like water vapor in the atmosphere, ice and snow cover, and temperature over land. In a warming climate, we would expect to see increasing or decreasing trends in each of these indicators. For example, decreasing sea ice and then increasing ocean heat content and increasing sea level. In the following sections, we'll focus on how Canada's climate is changing, and more specifically, Ontario climate. However, here it's worth taking a moment just to remember that across Canada and around the world, the impacts of change can be different. Starting at the national level in Canada, evidence has been gathered on warming. So Canada has warmed already and will continue to warm. And also, importantly, Canada warms about double the global rate. The oceans are warming and becoming more acidic with less oxygen. The effects of widespread warming are evident and projected to intensify. Total precipitation is projected to increase on average, with decrease in snowfall and increase in rain. And summer rainfalls may also decrease in some areas. Seasonal availability of fresh water is also changing, with an increased risk of water supply shortages in summer. Importantly, weather extremes are expected to intensify, and the rate and magnitude of climate change under high versus low emission scenarios project two very different futures for Canada. So an immediate question or reaction would be, so what difference would a degree or two of average temperature change or a 5% increase in precipitation, what difference would they make? So here it's important to consider that small changes in average conditions mean big changes in extremes. So under a warming climate, we'll be seeing fewer cold extremes, more heat extremes, and also more record-breaking heat extremes as the frequency and intensity of these events increases. For Ontario, the temperature has measurably increased already compared to recent baseline periods, and that's true both for averages and for extremes. Importantly, also, winter temperatures are increasing faster than summer temperatures. So that's why we're seeing fewer cold extremes, because during the winter months, more warming is observed. In Owen Sound, for example, the number of days per year over 30 degrees is projected to increase from 8 to over 19 by mid-century. And that's in a moderate scenario, and even an even greater increase is projected according to a high scenario. With regard to precipitation, we see higher and lower levels of change depending on geography. For example, how far the community is with respect to the Great Lakes. And precipitation is also not uniform by season, with most increases occurring in the winter and fall. So what we have seen so far is that precipitation is increasing. Some areas more impacted by those increases than others. About an 8% increase has been observed between 1979 and 2016, and that ranges from 4.3 increase in the summer to 24% increase in the winter precipitation. So there is a definite seasonality to the increase, and largely that is because more precipitation in winter is falling in the form of rain rather than snow. Some of the precipitation projections include an overall increase, again, concentrated in the fall and winter, with summers most likely becoming drier than they have been. Important regional considerations include increased lake effect snow and rain. Dry summers with the higher frequency of intense rainfall events are likely to lead to multiple impacts like flooding and erosion. So even though generally we expect it to become drier, but there will be a higher number of extreme events where large amounts of rain would fall on dry soil and cause adverse impacts. So here, just elaborating on this, a flood is the costliest disaster type throughout Ontario. And here we see combined effects of changing seasonal patterns, extreme events, including both long and short duration extremes. And as winter warms, we're also more likely to get rain on snow events. And of course, the impacts are most important for the infrastructure, and when infrastructure is aging and weathered, it has increased vulnerability. Some climate indices like temperature and precipitation are easier to discern change historically and projected, while complex events like freezing rain pose multiple challenges. So based on related trends like moisture conditions and temperature trends, climatologists are saying that there's likely to be an increase in frequency and severity of ice storms and freezing rain events, with significant damage occurring specifically to infrastructure, which increases dramatically above certain thresholds of accumulation, and a combination of freezing rain and wind and also aging infrastructure can exacerbate failures. We are expecting to see more strong wind events and longer tornado seasons, and I think we've seen those in different parts of the province in recent years, in Ottawa, as well as near Lake Simcoe and along the coast of Lake Huron. There's the potential for stronger wind gusts, specifically during storms and thunderstorms. So one study indicated this is expected to be a 50% increase in the number of events with wind speeds over 90 kilometers an hour by 2050s. And importantly here, small increases in wind extremes have the potential to bring large increases in damages, because wind speed and damage are not linear, and above certain thresholds, damage increases rapidly. Great Lakes water levels, importantly, are affected by changes in precipitation and evaporation rates. Under a high emission scenario, projections indicate higher lake levels and also greater variability, so we can expect lower lows and higher highs. And these have been prominent in the past decades, where we've seen really low levels and followed by very high levels. Snowbelt regions in Ontario are observing increased lake effect snow. When warmer water combined with the decreased ice cover leads to increased severity and frequency of high impact weather events. To recap here, obviously it's warmer already. By mid-century, the changes will be further amplified. Changes in temperature and precipitation averages, annual totals, only tell us part of the story. But importantly, there are changes in seasonal variation, warmer winters, wetter winters, drier summers, more variability, and also more extreme events. But specifically, some changes that are projected is an increase of over 20 days over 30 degrees Celsius by mid-century, 70% fewer frost days, a significant increase in the growing season by up to 9 more weeks, doubling of heavy precipitation events, and again, as I said, more weather variability in general. So here I'll briefly talk about the impacts and focus on agricultural impacts specifically. But starting with the infrastructure, more intense rainfalls, snow and ice storms are responsible for numerous impacts to infrastructure, like loss of roads, airport and bridge assets, also underground utilities, premature infrastructure deterioration, issues with water treatment and wastewater, widespread power outages, and then risks of collapsed buildings, transportation delays, and so on. And importantly, these impacts do not occur in isolation. When a severe event occurs, multiple systems are impacted. Higher temperatures and stronger winds also lead to power outages, compromise structural safety, damage to buildings and utilities, energy shifts, premature infrastructure deterioration, and more. There are important health implications of that the changing climate brings, with a wide variety of impacts related to heat, air quality, and safety due to fire and flood. Both physical and mental health risks are important to consider. And there are also changes in climate-sensitive infectious diseases. So here, just looking at the risk map of tick-borne diseases and the range of areas affected by those, we can see that around 2,000 high risks and moderate risks mostly were limited to southern Ontario, and that's the risk of Lyme disease carried by black-legged ticks. By kind of like the 2020s, the entire southern Ontario is under high risk. Moderate risk has moved to the northern shore of Lake Superior, and then looking further into the 2050s, a significant portion of southern and to a degree northern Ontario will be under high climatic suitability for the ticks. Even more so, more pronounced by the 2080s. Ecosystem impacts, again, are important, and they are extensive, and these include changes in the timing of natural cycles, species range shifts, decreases in lake ice cover, shorter ice cover seasons, and also increased prevalence of invasives and more frequent pest outbreaks. The change of suitable habitat will affect distribution of species on a large scale. So, for example, the core climate range for white spruce is expected to shift northwards as temperatures increase, and spruce in this is not unique. The climate to which different plant and animal species are adapted is steadily moving away from where the species' geographical habitat traditionally is. And so for a lot of species, especially the plants, it's difficult to keep up. For agriculture, climate change could bring new opportunities in the region, such as longer growing seasons, grazing seasons, increased yields, and potential to grow new crop species. But at the same time, it could also put pressure on the ecosystem, damaging crops, infrastructure, and resulting in increased production costs, soil and water quality degradation. So some other positives would include reduced heating demands in winter and more species diversity, but at the same time, plant damage and disease susceptibility are projected to increase with more extreme heat events. Livestock mortality increases, and decreased productivity are expected related to heat stress specifically. Some of the major drivers of agricultural impacts in the region, Grey Bruce and Huron counties, include drought, heavy precipitation, and flooding, extreme heat, also spring and fall frost, and variable weather. So major impacts coming as a result of the drivers, they were identified and are shown here for key components of the agricultural sector, including field crops, farm operations, soil and water resources, and also on the subsequent slides, livestock. So drought, as we can see, primarily is key for field crops and soil and water resources, and that's manifested by delays in plant development, reduced yield, nutritional value, decline in soil suitability to support plant growth, also poor nutrient uptake, increased water contamination, and low water levels that lead to greater irrigation demands and higher production costs. And so some of these are indirectly impacting livestock as well, with specifically reduced yield and nutritional value of plants that are used as feedstock for livestock. Flooding and heavy precipitation is another major hazard that affects farm operations and has the potential to damage infrastructure, field crops, soil and water resources. So here, severity and frequency of heavy precipitation and flooding events have both increased due to the combination of shifting spring snowmelt regimes, increasing rain on snow events, and then more long duration heavy precipitation events and more short duration increased storms. Spring and fall frost is more important to perennials and crops like winter wheat. And some of the impacts are compromised fall hardening and reduced yield. Extreme heat is a particular concern for livestock and potentially can cause decreased feed intake, slower weight gain, lower milk production, and also reduced fertility and increased mortality in livestock. Variable weather, and also so specifically fall and winter weather, compromises fall hardening and increases sensitivity of crops like alfalfa and winter wheat to freezing temperatures, makes fruit trees more prone to winter injury, ultimately reduced yields. And also warmer winter weather leads to increased chances of pest survival. And that in turn has cascading effects like increased pesticide application and higher production costs and greater chances of contamination of water and soil. So as I've mentioned already, it's important to recognize that impacts are not isolated and constrained. Impacts on one region can have ripple effects in others. Physical impacts can often lead to economic consequences. So impacts on crops and livestock lead to decreased yields and affect the bottom line. And additionally, repeated stresses and failures in system can also increase vulnerability, making subsequent failures more likely. So some of the different types of climate change impacts as listed here. So some are slow emergent. Others are related to widening climate variability, extremes, combined impacts, and also surprises, the unknown impacts from atmospheric changes. So key messages at the end of this section is that climate is different from weather, and climate change is attributed directly or indirectly to human activity that alters the composition of the global atmosphere. Canada has started to warm and will continue to do so at double the global rate, and significant impacts from climate-related events are already being experienced and need to be planned for. Changes in climate are causing some slow onset or gradual impacts, as well as impacts from acute events like storms and floods. And impacts don't occur in isolations, and often risks and impacts are interconnected and overlapping. So briefly pause here, catch your breath, and see if there are any questions at this. And if there are no questions, we will continue. And in this section, we'll review existing vulnerabilities. So in other words, livestock sensitivity and exposure to climate hazards, So here, it's important to begin with some understanding of how different terms relate. Vulnerability to climate change, and therefore the risk associated with climate change, is a composite of multiple different factors. And that's important to evaluate and consider each of these elements. So we're talking about potential impacts that may occur without considering adaptation. There's exposure. In other words, the nature and degree to which a system is exposed to significant climatic variations. There's sensitivity, which is the degree to which a system is affected either adversely or beneficially by climate-related stimuli. And then adaptive capacity, which is the ability of a system to adjust for moderating damages, taking advantage of opportunities, or coping with consequences. So as we can see, impacts, exposure, and sensitivity contribute to vulnerability, whereas adaptive capacity is there to alleviate some of the impacts. When we're using a vulnerability approach to risk assessment, or we focus on identifying areas of vulnerability within communities or different sectors and determining the thresholds of impacts, it is important to engage with the community and seek local knowledge here in order to determine where impacts have been experienced already, understand when and where they're realized and what the thresholds are, and then understand what strategies to cope exist and identify solutions to adapt and build resilience. Livestock and also crops produced across the province are inherently vulnerable to weather and climate conditions due to their direct exposure. And for each of the risk scenarios in our previous work, we have documented sensitivity factors that determine the level of vulnerability of different ag sector components that are shown at the top. So crops, livestock, fruit and vegetables, and then soil and water resources, as well as farming operations. So vulnerability of these components to various climate hazards, like drought, variable weather, increasing temperatures, and so on. So for livestock, vulnerability factors include higher metabolic rates, high susceptibility to changes and rapid increases in temperature, also age and immune status of livestock. So older and younger animals are more vulnerable to heat. Also, those that have recently been sick or just generally have a weaker immune system, they're also more vulnerable. And we're talking also about pregnant animals that would be more impacted by extreme events and climate impacts. The level of exposure to weather elements is also important. So some of the elements that are in the indoor systems, they tend to not be as directly impacted by climate change. So there are indirect impacts through infrastructure, but there is no, since they're not outside, they're not directly exposed and affected. For soil and water, poorly managed soils and also soils with lower density are more likely to be adversely affected by drought. Specifically, soils on greater slopes are more vulnerable to erosion that's caused by heavy precipitation events, and proximity of fields and pasture to water bodies determines also the level of potential water contamination by runoff during heavy rainfall. Some key elements here are that climate change represents a wide range of immediate impacts and long-term shifts with profound implications. The consequences are uneven, and our actions should acknowledge and address differences in vulnerability, sensitivity, and exposure. So there's been quite a bit of information. I suggest that we pause for a minute or two just to stretch and breathe and consider what we heard. Reflect, ask any questions before we continue to talk about adaptive capacity and then specific management practices and solutions to increase resilience to climate change. Okay, if there are no questions at this time, after a brief pause, we move on to the topic of understanding adaptive capacity and resilience. Understanding the potential and need to adapt to immediate risks is important, and finding pathways to adapt and be sustainable through the long-term changes is equally important. So we will review the concepts and examples of resilience and adaptive capacity here to learn more about these issues. Resilience refers to the capacity of a system or sector to withstand or to recover quickly from difficulties. And adaptive capacity is the ability of a system to adjust for moderating damages, taking advantage of opportunities, or coping with consequences. And there are 4 principal categories for assessing adaptive capacity. And specifically, these are technology, resource availability, governance, and sector complexity. On the surface, one might say that resilience and adaptive capacity in systems seem very similar. And one way to remember the difference is that resilience is a broader system property. We can say that a region's food system is resilient to drought, kind of as a more general statement, if we think that for a number of reasons, the food supply would be able to continue mostly without issues during a drought. And meanwhile, adaptive capacity is more narrowly focused on specific skills and mechanisms that are deployed by human systems to contribute to resilience. In other words, we might identify that the system or component of the system is resilient, and then identify sources and mechanisms of resilience in terms of particular knowledge, practices, land uses, biological properties that are functioning in the food production system, and referring to these as adaptive capacity. We'll now look at the 4 principal categories in more detail, starting with technology, which refers to machinery, equipment, or knowledge that can support the resilience of a system. Some examples of technological advancements include GPS guidance for field equipment, precision machinery, advanced drainage and irrigation systems, livestock genetic research, and more. The agricultural sector is known for adopting new technologies to assist with production and productivity. So some examples would include GPS guidance and drone technology, advanced, again, so as I said, advanced drainage and irrigation systems, precision machinery. The technology category of adaptive capacity also includes sectoral best practices. and planning that will be discussed in more detail further on. It should be noted that some of the technological adaptations may require significant improvements of infrastructure, for example, greenhouse facilities, water sourcing, and energy systems. And these improvements have time and cost implications that are important to consider. Resource availability relates to financial, human, and natural resources that are available to an organization or industry or system. From a financial resource perspective, the Canadian Agricultural Partnership, which is a 5-year and $3 billion investment program in Ontario, is a primary financial support mechanism that is used to stimulate growth in the agricultural sector. And although Canadian Ag Partnership does not offer dedicated funding for adaptation actions, it does include climate change as one of the 6 priority areas at the national level, with opportunities of covering costs for research initiatives and programs around building climate resilience across the sector. AgriCorp is an agency of the Government of Ontario that delivers several business risk management programs, like agri-stability, to support Ontario's agriculture producers by offsetting financial losses and protecting producers from large margin declines that are caused by a combination of production losses, adverse market conditions, or increased production costs. So these are the crop insurance people in the province. Another example would be the Environmental Farm Plan, the Canada-Ontario Environmental Farm Plan, that is a resource available to farmers to offer guidance, to complete risk assessments, and develop and implement action plans for addressing environmental issues that are relevant to their farms. And this is very fine scale and farm specific. Additionally, natural resources and related ecosystem services play a vital role in agricultural operations through their flood and erosion control and water filtering, and increased protection and conservation of ecosystem, especially in the southern regions of the province, where increasing urban development is occurring and poses pressures. So in those areas, increased protection is imperative to increase capacity across farming infrastructure, technology, and operations to better cope with emerging climate risks. Governance and sector complexity are the final 2 components of adaptive capacity, where governance notes the level of political or administrative presence and its organization and function to support resilience within an organization or industry, while complexity relates to the number of stakeholders or decision makers that are present in a sector at a regional level. Several governance mechanisms, policies, and institutions exist to support agricultural production in Ontario. Climate adaptation activities include long-term planning for potential water shortages, monitoring and surveillance programs for emerging crop and animal diseases and pests, and also supporting research into business risk management approaches, and enabling demand-driven knowledge transformation and knowledge transfer through dialogue, collaboration between researchers and farmers. And depending on the region, various policies and programs exist that could enable adaptation measures. So a lot of the work that's done by conservation authorities, the rural water quality programs, land protection designations, and so on. Speaking about the complexity of the sector, so in Ontario, the ag sector is highly complex and involves several key players and is influenced by a number of external and internal forces like commodity prices, financial markets, available technologies, health safety regulations, and institutional support. All of these contribute to adaptation decisions and affect the overall adaptive capacity. And there are different levels of control over certain adaptations, with some available for implementation at the decision of a single operator, while others are shaped by multiple stakeholders in farming and government and elsewhere. just going to stop here really briefly to see if there are any questions or reflections. As we move on, we will discuss some of the key adaptation responses and best management practices that exist in the ag sector, focusing specifically on livestock. So here it's important to say that successful climate adaptation planning requires the integration of multiple elements. We have spoken about climate conditions, vulnerabilities, capacity to adapt and to cope, and also adaptation measures and monitoring. So kind of looking at what level of capacity people, policy, and infrastructure have to absorb the consequences from changing climate conditions and make timely adjustments, and what actions will be effective and provide value, and how will improvements in resilience or reductions in vulnerability be measured. Here, I should say that while developing an adaptation plan or program is important, and it helps to ensure that there's coordination when we're addressing particular challenges, but adaptation can also occur on a project-by-project, day-by-day basis. So there are actions that an individual farmer can accomplish, a farmer or a group of farmers, without a comprehensive plan necessarily. For all scenarios in the risk registry, we have recorded adaptation strategies and risk solutions that range from incremental adjustments of existing practices to some major alterations that can transform the entire farm operation. On-farm infrastructure, technology, and best practices significantly influence the resilience of individual operations. Producers implement adaptive measures on a regular basis and seek new technologies to better manage on-site climate risks. So the following on-farm practices can significantly increase capacity to respond to and cope with climate-related risks. So it would be, and these are all livestock focused. So they are a selection of breeds with resistance and tolerance to extreme climate conditions, like heat, for example, or drought, implementation of heat and cold abatement techniques. So that's both for indoor and outdoor livestock systems, nutrition management and diet alterations, proper monitoring to be sure that any issues are caught early on and addressed, adjustments to handling, transportation, and grazing management, such as rotational grazing specifically, participating in production insurance programs provided by AgriCorp, for example, and also retrofitting facilities and infrastructure. And here we're talking about capacity in barns, storage buildings, so where feed is stored, and so on. So talking specifically about beef and dairy and adaptation best practices. So here we know that milk production yields are most affected in the summer when high heat days impact cattle. So to avoid this, avoid the season and increasingly warmer temperatures with climate change, it is important to adjust the timing of birthing for the fall and winter months to avoid peak milk production occurring in the summer, considering the use of precision technologies to monitor reproductive activity and tracking behavior. Important here to talk about management-intensive grazing. That refers to practices where animals are allowed to graze only on a small portion of pasture at a time, while other areas rest and recover. So that's especially critical in dry conditions. This form of grazing management should be encouraged through use of time control and shortened grazing periods, and also increased animal density per paddock. when we're talking about cold conditions. Some best practices can also occur specifically during transport. It's important to make sure that livestock is protected from precipitation and from wind that blows into the sides of the truck, as it increases their loss of heat and can cause hypothermia, even if temperatures are above freezing. So there you would supply ample bedding and insulation and avoid overcrowding, kind of to allow animals to reposition themselves, avoid frostbite. And then there's the importance of making sure there's adequate ventilation that exists during transportation. For general treatment and handling strategies, so again, as was mentioned before, there's close monitoring of animals for sign of heat stress and cold stress, relocating animals to a sheltered area when needed, providing shade, and providing adequate nutrition, so extra nutrition in cold conditions, and then ample water when it's when conditions are hot. So for dietary supplementation specifically, this it is important and can aid in animal health, well-being, especially during high heat events, and that can include adjustments of feeding rations, manipulating the amount of fat and fiber in diet, adding appropriate amount of nutrients, vitamins, electrolytes, and more to the diet. And here one should also consider adjusting food and water schedules. For example, feeding cattle in times of day when they're not exposed to extreme heat. So either early in the morning or after dusk. For hogs and poultry, and that's the kind of like the indoor management systems, some of the key and relevant best management practices relate to transportation, and they have been mentioned. So making sure they're not exposed to heat and cold conditions during transportation, also during loading and unloading. If it's too hot and too cold, perhaps consider postponing transporting them if possible. Also making sure that conditions inside the barns are adequate in heat conditions, sprinkling water to allow so pigs specifically to cool off, making sure the bedding is clean and changed regularly, and again making sure that ample water is available and food is adjusted, both the type of food that is offered and the amount of food and the timing of food that is offered. There is a lot of great work that is being done in the field of adaptation and best management practices. Some of the things that we have heard is that it's important to regularly talk about what people's experiences with BMPs are and the direction things are heading for climate change, kind of presenting case studies that relate specifically to observed and expected climate trends. So what we heard is that conversations should be resonating with people and make more direct ties with local and regional experiences. And that's the best way to understand. A document that was developed lists a number of case studies and provides details on how some local farmers have successfully adopted best management practices and alternative land use solutions in the region. So farmers in the area have successfully implemented some BMPs, which have helped them to reduce soil erosion and nutrient runoff, also protect overall soil and water quality, at the same time providing several economic benefits of applying these practices, including increased productivity and lowered operating costs. Featured case studies include management practices adopted in the Gully Creek watershed, which is located in the Osable-Bayfield Conservation Authority.
And I think your audio cut out. Can you hear, Shannon, or was that me? Is that on my end? You can hear? Okay, maybe it's on my end. Sorry to interrupt.
No worries. Although it did just give me a message that the internet connection is unstable, and I'm not sure. But
you're back.
Yeah, do let me know. I am back. Okay.
Maybe it's on my end. Yeah, sorry.
Okay, no worries. No, thanks for raising it. If there are any issues, yeah, make sure to mention them. So I was just talking about the Gully Creek watershed and how it has been the place where since 2008 a number of BMP implementation and monitoring has occurred. So specifically, it has been the site of streamside restoration, riparian tree planting, conservation tillage, cover crops, precision agriculture, as well as manure amendments and nutrient management. The implemented best management practices have collectively reduced pollution transport and nutrient loads that enter the Gully Creek watershed, and the project has increased broader awareness around the importance and associated benefits of BMPs to improve soil and water health, at the same time not compromise agricultural productivity. Local farmers, as mentioned, have also participated in the ALICE program, or Alternative Land Use Services program, and reported on the benefits associated with production and ecosystem health. The ALICE Grey Bruce program aims to support land stewardship by offering incentives to implement projects for enhancing ecosystem and watershed health while maintaining or improving agricultural productivity. And here an example of the ALICE project featured here is big rock bison, and that's an environmentally minded bison raising operation in Shallow Lake, where grassland across 200 acres has been restored on the family's agricultural operation. The owners joined ALICE in 2017 to contribute to local riparian and habitat conservation. This local farm, located in Grey County, has worked to conserve their land by limiting access of the herd to certain areas, allowing increased habitat function and general ecosystem health. So we have covered the larger portion of content for today, and before we dive into a group activity, I suggest we make a pause here for our group activity and discussion. The way we will start, so I'll introduce a scenario, kind of like a fictional scenario to reflect on. And we'll then at the next slide look at a couple of tasks, a few questions to answer, and just reflect on any management practices and solutions to the issues that a farmer is having. So the scenario is that you're a beef farmer whose farm is located in Bruce County, and it is approximately 150 acres in size. So it's a cow-calf operation, 75 cows, 25 calves, several goats, small open pasture for grazing, some forage crops growing for the animals, and producing about 800 tons of dry hay a year. So about 2/3 of what's required to feed. So, and purchasing the rest. The farm also has some cash crops, as well as a mature woodlot and a small wetland that are home to a variety of plant and animal species. What has been happening over the past years is that hot conditions have had impacts on the health and productivity of the herd, with calf vulnerability being a particular concern. Several years ago, summer drought conditions resulted in loss of over 50% of the hay crop, making you purchase feed from another farmer in a different location at a high price, causing challenges to ensuring the health and caloric needs of the animals. And now you're looking for possible solutions to alleviate the issues, build climate resilience, and at the same time, not compromise economic productivity. So here, it's kind of like a mock-up of a map of the farm, right? So some cornfields, barn and facilities, the farmstead, bit of a pasture, largely forage crops, and then the woodlot and the wetland located there. So why don't we reflect on this scenario and see what observed changes in climate and whether patterns have been, and which hazards, in your opinion, would be the most impactful to the farm now and in the future, and what additional impacts might be of concern. So as a refresher, so this is some historic and projected trends, just to inform the discussion. And consider what the issues going forward might be compared to what they have been. Yeah, I thank you very much for joining and for the interest and the questions, contributions to the discussion.